All right, so this is going to take you guys through the homework assignment for radiometric dating. So we're in our Unit 7, Lesson 2, that first explore. So hopefully you've watched the video that talks about what we're looking at here in terms of different decay rates for different atoms. For this first one, we're looking again at this band of stability where we have this balance of neutrons to proton ratio, and the heavier elements are going to go through alpha and beta decay to form more stable elements. And so you can look at the chart up there to kind of see how that would work. But again, this idea of looking at thorium-232 and seeing where it is on that graph, and then either needs to gain or lose protons to become stable. This is what we're going to look at a little bit further, and you saw a chart of it in our slides. This idea that uranium is going to go through different alpha and beta decay processes to try to stabilize over time, eventually formulating lead. And so we can take that to determine age. And if we think about that process of going from uranium to lead, the more lead that we have in a sample, the older that is because it's had a longer time to have that decay process happen. So this chart is showing you that we'd expect sample A to be older because it has a higher proportion of lead to uranium. All right, when we get down here to these components, we can talk about how we do this with organic materials, so looking at carbon-14. This gives you the half-life, and it gives you the parent and the daughter isotopes, and it can show you kind of what the half-life is. So anywhere from almost 6,000 years to 50 billion years, and how those could each be used for different types of materials. So it gives you crystals, it gives you a wooden sculpture, and it gives you a meteorite. And so you want to think about which of those pairings would make the most sense based on those half-lives to determine the proportions of the parent to daughter isotopes, and then what that would be in terms of age. So if you just look at the age component of it, you can see their process. So they're using uranium for the crystal, right? If we have uranium, that's going to give us the approximate half-life for that crystal where is about 4 billion years old. If we're looking for wood, we're going to use carbon-14 to nitrogen-14. And then if we're looking for a meteorite that doesn't have any uranium, we're left with this one. So this rubidium to strontium-87 component. All right, and then for our one here, we're looking at a bone which has carbon in it, and it was found in the La Brea tar pits in Los Angeles. If 70% of the fossil, if it's gone, we want to think about how many half-lives that's gone through. So it would be easy if it was 50%. We know we go through one half-life. It must be more than one half-life as 70% is back. So we're just going to approximate. We're not going to use any natural logarithms to solve these. You can if you want, but the approximate is it's more than one half-life, closer to two half-lives, and so we're going to use that half-life for carbon-14 of 5,730 years, and basically not quite double it and have an approximation of 10,000 years old. All right, you don't have to do the hands-on lab. If we were in class, we would do something like that, but that's not something you need to do at home. And let's see, all of that goes to there with your hands-on lab. The last piece here is this idea of absolute age, specifically in rock, and at what point do we have this radiometric dating start for a rock. And for a rock, it's going to be when it cools down and hardens. So we have this transition from magma to rock, and that's when we're going to start this process of unstable isotopes going through their decay process and becoming more stable. All right. This again shows you the chart for carbon-14, carbon-12 to carbon-14, this idea of when a organic material is no longer alive, we can start to take these ratios of carbon-14 to nitrogen-14 ratios and figure out how long that has been dead. These are the answers to that last paragraph there, and then this is just a picture showing kind of this process in a more scaled up view where they have a machine that's going to measure those ratios. All right, that's it for this one. Hopefully those made sense. Again, if you have any questions, feel free to reach out.